we consider now what we call as non-steady unidirectional flow. So now we have introduced the situation whereby the fluid flow is unsteady. That is, it does change with time. So as in one of the earlier problems, where u was different from 0, but v and w, that is x and y components, were 0, the pressure was 0, and so on, the equation of motion becomes of this type. You will remember this is a famous equation that we come across in problems of, again, mathematical physics and chemistry, and a number of places, the heat wave, heat equation, wave equation. It is commonly known as diffusion equation and so on. So we see this equation in many places of the problems that are associated with physics and chemistry. It's not an unknown equation for all of us. So its solution are found, it's a standard solution. In a fluid flow situation, we only have what will change the solution? What will affect the solution? The solution will be affected by the initial conditions, by the boundary conditions, and so on. So that's all that we have to do. Otherwise, solving this equation, the technique is the same. We only have to find out the arbitrary constants that are generated after integration by substituting the appropriate boundary condition, and that will give us the required results. So the mathematics, therefore, is very standard, and we obtain the equation to be of the form chi is equal to 1 over 2x into nu t to the power half times exponential of minus y square divided by 4 nu t. So you can see that the solution is dependent on this part, exponential e to the power minus y square over nu t times some constant, of course. That doesn't make much difference. So the thing to consider it is what happens when y increases, what happens when the time t increases. If y increases, then this number becomes small. If t increases, then this number becomes large because of the negative sign that is there. Anyway, this equation is a typical answer to our diffusion equation, and it satisfies that equation identically. And of course, we need to apply these conditions to the solution. Chi is, it tends to 0 when t tends to 0, and of course y is different from 0. I mentioned here that y is a variable. Its increase or decrease is going to affect the solution, and that is exactly reflected in these boundary conditions. And chi tends to infinity as t tends to 0. So I did mention that if t becomes small, this number becomes large, and that's what it says here. Therefore, chi becomes, it tends to infinity as t tends to 0 when y is equal to 0. And with the condition that we impose, that between minus infinity to plus infinity, chi into dy is kept as equal to 1. And the last property is due to the standard formula that we have in the solutions of partial differential equation that are given by this. And if the fluid occupies the region from minus infinity to plus infinity, as we have defined earlier, and we allow the velocity at time t equal to 0 to be prescribed function of y, then u of y will be some function of y. And we can write it as in this form. And again, of course, with a little algebra and manipulation, we put the limit that t tends to 0. If t tends to 0, then u, the velocity components, become equal to this function that we have defined, f of y, in this limit. So that's all the description of fluid flow situation of non-steady unidirectional flow. And really what have we seen is that it amounts to solving the diffusion equation or partial differential equation of the fluid flow problems boundary conditions.